Where are you going?
All right. So nitrogen. Yes. What is this?
Can we play prank on them when they come back in 17 minutes, please?
Can we play what?
Yes.
What do you want to do?
They want to scare them basically, like hide and pretend that everybody left, so that way they think that they were late.
And like we'll put an announcement on the
I don't want practical jokes.
Can we?
All right. This is a very. I think. Oh, I don't want to get myself recorded, so I'm going to continue to teach. All right. Anyway, so let's look at nitrogen. All right. Nitrogen will not take or give. Nitrogen instead will form a covalent bond. And we said covalent bonding is what? Covalent is sharing of electrons. Covalent is sharing of electrons. All right? So when two nitrogens come together, so this nitrogen has 5, the other nitrogen has 5. So how many of the electrons are not paired up? In each atom of nitrogen, 3 electrons are not paired up. Do you see that? So these 3 electrons will pair up and the resultant structure of diatomic nitrogen looks like that. Alright? It forms 3 covalent bonds. Between the atoms it moves and the 3 of them, the 3 single electrons pair up with each other. Is it making sense so far? Okay? So similarly, we have oxygen. Oxygen has how many electrons around itself? It has 6. How many electrons are not paired? 2. So what will happen to these 2 electrons? They will pair up and they will form a bond. Now we also talk about octet. Is that right? So if you look around nitrogen, let's count. 2, now remember that is a pair. Is that right? 2, 4, 6, 8. You see that nitrogen has 8. This nitrogen also has 8. This oxygen, 2, 4, 6, 8. And the other oxygen also has 2, 4, 6, 8. By coming together, by forming the covalent bond, they have 8 each. Yes, John?
How does them? Oh, okay. You just explained that they formed to make 8. I was like,
Yeah.
that's 4.
Does that make sense? Now, this pair of electron is called a lone pair. Alright? This pair of electron that is shared is called a bond pair. That which is shared between the 2 atoms is called a bond pair. That which the element keeps to itself is called a lone pair. Yes?
The nitrogen one doesn't go up to 8.
No, remember, each one is a dot.
Oh, okay. The bonds kind of.
How many now? Between them? 6, and then it has 2 of its own. Does it become 8? You understand? And each oxygen will also have 8 by coming together. And so, yes.
Just a question.
Yes.
When you're when you're labeling the dots, do you start here and then go this way?
Yeah, that is correct.
Okay.
That is correct. Okay? So, but then when you start drawing loose dot structures, remember, there should never ever be a single dot on any element after it's made the compound. Does that make sense? Now it's paired up. Is there any single electron? No, you should never ever have a single electron. Does that make sense? Okay. So at this time I would like to answer another question that we actually had on the last unit. Remember, magnesium reacted with oxygen in the air to form magnesium oxide. Do you remember that? And I do remember a discussion, okay, when magnesium is burning, it's a combustion reaction. Is that right? So what is required to burn? Because we're saying it requires oxygen. But well, nitrogen is also the dominant portion of air. How much of air is nitrogen? What percent of air?
97?
No, not that high.
46.
Yeah, almost 80%, 79%, almost 80%. Like 20% or less than that is oxygen. Is that right? So here is a question for the class. Why does nitrogen prefer to react with oxygen, which is only 20% of air, but it doesn't react with nitrogen, which is like 80% of air?
Because 80 plus 20.
No. John, think about what you're answering. I'm asking, why does it choose to react with oxygen instead of nitrogen? Because they add up to 100? What answer is that? Why does it choose to react with oxygen? Because
the bonds
uh-huh.
make it strength.
Don't listen to Vishwa. You think on your own. You were thinking right.
So it does that.
Why does it choose to react with oxygen and not with nitrogen?
Because the bonds make it eight.
How many bonds? Look at the bonds. Compare the bonds. Why does it choose to react with oxygen and not nitrogen?
Less bonds.
Less bonds.
Let him think. Give him that opportunity. He's so used to it that he's not thinking.
Oh, okay.
What is happening now?
So it reacts with the oxygen and not the nitrogen because the oxygen has 4 and the because N isn't a thing, not a compound.
No, the one in between is a bond.
Yeah.
So how many bonds does oxygen have?
2,
How many bonds does nitrogen have?
3,
How many bonds must be broken for nitrogen to react?
2, a lot more.
A lot more. Why does it not react with nitrogen but with oxygen?
Because it's lazy. It doesn't want
Ah, because it has to break more bonds, which means it requires more energy. All right? Yes.
How do you tell how many bonds there are?
We draw the Lewis dot structure that helps us determine the number of bonds. Okay? Is it making a connection for you? So, Joanna, how many bonds in oxygen? How many bonds in nitrogen? Which takes more energy to break? Nitrogen. Therefore, it requires more energy to break those bonds. So, when it's heating up, the oxygen in the air will break up faster, therefore, or quicker because it requires less energy, and therefore magnesium will dominantly react with the oxygen in the air. Is that making sense? So all this is interconnected. Does that make sense? We don't learn things in isolation. We're trying to explain why they happen the way they happen. Alright? So this is one example of why we need to know Lewis dot structures. Does that make sense? Okay? Now, let's do some examples. There are some rules that you have to follow when you draw Lewis dot structures. I showed you single atoms or electrons that join together and make the bond. Is that right? Even though that looks easy to follow, that's not always the case. Alright? So let's take an example. Let's take ammonia. Let's know the difference between ammonia and ammonium. They're not the same. What is this? This is?
Ammonia.
What is this? Ammonium. They're different from each other. Ammonia is a neutral gas. Alright? It's a neutral substance and it's a neutral compound and it's a gas. Whereas this is a polyatomic ion which can exist in solutions only. Does that make sense? They are very different from each other. Do not get confused. Okay, so I have to draw the Lewis dot structure of ammonia. How am I going to draw that? Alright? So here is We call this, I think Miss Williams labeled it the communist rule. All right? What does a communist rule mean?
Everything's equal.
Yeah, so what happens is when these elements come together, all of the electrons, valence electrons are taken up and then they are redistributed so that the elements have the 8. Does that make sense? So, what is my step 1? My step 1 is I will count the number of valence electrons. How many valence electrons does nitrogen have? Nitrogen has how many valence electrons? 5. Hydrogen has how many valence electrons? 1. But how many hydrogen atoms are there? 3. So each one will contribute 1. So plus 3, which becomes what? Which is 8. Okay? So now what we have to do is, I think I can wear those microphones. Hopefully my voice is so loud that it will pick up. Alright? So now we have to arrange the elements in the compound so that we can draw the Lewis dot structures and distribute. So step 2, make a skeletal arrangement. Make a skeletal arrangement. Alright? What does that mean? I have 1 nitrogen and 3 hydrogens. Skeletal arrangement should mostly be symmetrical. Alright? So what will I put in the middle? Which element will I put in the middle? Nitrogen. And then I arrange the 3 hydrogens around it. Now why do these elements come together? So that they can make a bond. So that they can get what they want. Is that right? So make a bond between them. Remember, each bond contains 2. So out of the 8 total electrons that I could collect, how many have I accounted for? 6. So there is 1 more pair of electrons that's left. Put that as a lone pair on the central atom. Alright? Now,
Electrons on the bond, valence, or not?
valence electrons. We count only the valence electrons. Now, hydrogen is happy with 2. Hydrogen is one of the exceptions that doesn't need 8. So hydrogen has 2, this has 2, that has 2. Count nitrogen, 2, 4, 6, 8. Is it a happy arrangement? Alright? So now we have to look at the shape of the molecule. Did we do an arrangement of shapes in the beginning? Alright. So now let's look at this molecule. Alright. And I'm going to show you the simulation that will help you understand the shape of this molecule. Now you kids can also Google that simulation at home. Alright. And choose shapes and play with it at home. You can download it and play with it. Alright. Now, so in ammonia, how many bonds did we have? 3 bonds, and 1 was we call that a lone pair. It was on nitrogen. Do we have 3 bond pairs and 1 lone pair? Alright? So let's insert 1 more bond pair here. Alright? But then there is 3 bond pairs and 1 lone pair. See, the lone pair also needs space. What does this arrangement look like to you? Well, but this is, lone pairs are not included in shapes. Pyramid. Does it look like a triangular pyramid shape? This is the base triangle and it's a pyramid. So what is the shape of this molecule that you have drawn? You will call it a triangular or trigonal pyramid shape. Are we good? Do we understand this? Alright? Make a skeletal arrangement, guys. I did not write the other steps. Sorry. So what is step 3? Have at least a bond. Have at least 1 bond between the elements, right? Between the elements. And then what is the next step? If there are leftover electrons, if there are leftover electrons, then include them as lone pairs where necessary, right? Where necessary. Are we good? All right. Let's do another example. Let's do methane, CH4. Can you kids try and draw the Lewis dot structure of methane?
Oh, yeah, we can do ammonia.
We'll do ammonium a little later. Okay? Let's do compounds first and then we'll come to polyatomic ions. Draw the Lewis dot structure. What is step 1? Count the number of valence electrons. Have a symmetrical arrangement. Alright, have at least a bond and then distribute the lone pairs if necessary.
Do the bonds also have to add up to
Yes, not the bonds. The elements, the electrons have to add up to 8. Alright? Is it 4 for carbon, each hydrogen giving 4, is it a total of 8? So if I choose a symmetrical arrangement, will I put carbon in the middle?
Yeah.
And I will arrange 4 hydrogens on the 4 sides. I need at least a bond between them. Is that right? Have I accounted for all 8? Carbon is happy with 8, hydrogen has 2, each hydrogen is happy. What is the shape of this molecule if it is surrounded by 4 bonds around it? Tetrahedral. This molecule is tetrahedral. Okay? Now, let's do water. Water is an abundant substance around us. Let's draw the Lewis dot structure of water and look at what that shape could be. Yes.
Would you put down multi-bonds?
We will do that in a little bit, not yet.
But not the one for this one.
I don't, you'll only need, try and do it first. Okay? So if I'm looking at this, each hydrogen is contributing 2, oxygen is contributing 6, I have a total of 8. If I want a symmetrical arrangement, I'll put oxygen on one side and I'll put hydrogens on both sides. Correct? I need at least a bond between them. How many electrons have I accounted for?
4.
Can somebody get the joke, please? 4. So how many more are left? 4. So how will we include the remaining 4? Should we include them as lone pairs? Is that right? So here is the lone pair and here is the lone pair. Yes?
Does it matter where we put the substituents?
That doesn't matter, that is fine. That is the correct Lewis dot structure. Alright? That okay, I'll tell you why that will also be correct. Alright? So if you draw it like this, or you draw it like this, alright? Or you draw it like this. All of these as Lewis dot structures are correct. Okay? It doesn't matter which way you draw. But I want my students to tell me what will be the shape of this molecule. Bent. Why do you say it is bent? Because it has 2 lone pairs. Okay? So let's go into this structure. Let's remove the bonds. And it has 2 bonds. Is that correct? And does it have 2 lone pairs? Yes or no? Remember we said we would not look at the lone pairs. What does this look like? Does it look like bent or angular? Does this look like bent or angular? Does that make sense? We don't look at the lone pairs. Is that right? If the lone pairs were not present, then what would the shape be? Say you remove the lone pairs. Remember, these are electron pairs, and electrons repel each other. Yes or no? They want to be as far away as possible from each other. So even though lone pair doesn't count for predicting the shape, it does impact how the bond pairs will be arranged. Yes or no? Does it make sense? Therefore, the structure of water will be bent. Alright? The shape of water is bent. Now, I am going to do one example with you, the next one. Water is common around us, so the shape of water is bent. Let's do carbon dioxide. You guys are right now breathing out carbon dioxide. We can't see it. But if you want to magnify it and see it, what would the molecule look like? Alright? So carbon is 4 valence electrons. Each oxygen is 6. There are 2, so the total is 12. And it's 16 total electrons. If I want a symmetrical arrangement, what do I put in the middle? Carbon. And now I have oxygen on either side. And I need at least a bond between them. How many bonds have I accounted for? 4. So that leaves me behind with how many more to account for? 12. So here is an extra step when you're drawing loose dot structures. Alright? So I will start by putting it on oxygen. So that has taken 6 and that has taken 6. 6 plus 6 I've accounted for all 12 electrons. But this arrangement is not correct. Why is it not correct? Because if I look at the central oxygen has how many electrons around it? How many electrons around central oxygen? 4. So carbon, not oxygen, that's why they're not answering. If the central carbon is heavily deprived in oxygen. Is that right? So here's the next step you will do with loose dot structures. If there is an element that does not have 8, alright, you will shift the lone pair and make it a bond pair. Alright? So this compound, now if I move it like that, there are 2 lone pairs on oxygen. Alright? I should see the 2 lone pairs on oxygen. Otherwise, does it become 8 around oxygen? 2, 4, 6, 8 is not there without the lone pairs. Yes or no? But right now, if I still don't transfer from here, oxygen is still 6. Is that right? So I'll transfer 1 more pair of electrons so that now carbon has 8. Does it make sense? Now carbon, oxygen, all of them have 8 each. Do you agree? So what is the next step? Once you fill in the extra electrons as lone pairs, you have to do your count. If any element is missing 8, then you need to move it around so that it becomes 8 valence electrons around each element. Lone pairs will become bond pairs. Are we good? What is the shape of this molecule? What will be the shape of this molecule? Does the atom in the middle have any lone pairs? No. So what do you predict the shape will be? It will be 3 atom linear, or just linear is fine, 2 atom. It will be a straight line. Now, when you are predicting shapes, please know this. Alright? So let me remove all this. Alright? We saw 2 bond pairs. Is that right? When predicting shapes, alright, This is called an electron domain. It's in the same direction. Is that right? It doesn't matter whether it's a single bond or a double bond. It will get oriented in a single direction. So for all practical purposes, this is only two bonds that will stay as far away as possible, and that will be a 180-degree angle. Does that make sense? This molecule is linear. Are we good? Okay? So let's do another example. So have we finished all of the shapes that you did so far? We did bend, we did trigonal pyramid, we did tetrahedral, we haven't done trigonal planar. Okay, let's do this example. Alright, let's say we are trying to draw the Lewis dot structure of formaldehyde that's used to preserve dead bodies, right? This compound is formaldehyde. Now, how do you count? Valence electrons for carbon is 4. Each hydrogen will give 1. That's 2. Plus oxygen is 6, making a total of 12. Now, there is carbon, there is hydrogen, there is oxygen. Which element will you choose to put in the middle? Why do we have a very large number of carbon-containing compounds? Carbon has how many valence electrons to begin with? 4. How many bonds can carbon make generally? 4 more. That's the maximum. Is that right? So carbon will always go in the center. Alright? So now I have carbon in the middle. I don't care where you put the 2 hydrogens. And then I have, on one side, on the third side, you will have oxygen. Do you want to complete the Lewis dot structure now? Okay, so I have at least one between the 3 that takes care of 6, so I'm left with 6 more to account for. Is that right? Minus 6, that gives me 6 to account for. And the 6 had to go as lone pairs. Is that right? Will I choose to put lone pairs on hydrogen? Does hydrogen want more than 2? No, it's only oxygen that wants it. 2, 4, 6. Now let's count around oxygen and carbon. Oxygen looks fine with its 8, but is carbon happy? Carbon has how many? 6. So what is the next step? Convert your lone pair into a bond pair. Right? So that will become a bond pair. Now, I should not see structures where you just keep transferring and you make any number of bonds you want to. That is not allowed. Carbon cannot have more than 8. Right now, if you transfer one more lone pair, does it become 12 around carbon? Yes or no? If I make that a triple bond. Yes or no? That's not allowed. 2, 4, 6, 8, 10, sorry, not 12, right? Is that right? Not allowed. So, you will have a double bond and 2 lone pairs on oxygen. Does that make sense? What is the shape of this molecule? How many bonds in how many areas is it distributed? Distributed in 3 different areas. Do you see that? This is an electron domain. This is another electron domain, and that's another electron domain. So what will be the shape of the molecule? Trigonal. Is there anything to push it down? Any lone pair?
Triplanar.
It's going to be trigonal planar. The molecular shape will be trigonal planar. Now, so we said there is a large variety of carbon compounds around us. Is that right? Whenever you're given carbon compounds, let's do the rule honk for carbon compounds. Honk for carbon compounds. Honk for carbon compounds. What does that mean? Hydrogen will form how many bonds? 1. Oxygen will always form how many bonds? 2. Nitrogen will always form how many bonds? 3. Carbon will always form 4. Now please remember, since carbon forms 4 bonds, you will never will have lone pairs, because all of them will be bond pairs. Does that make sense? You can never form a structure with a lone pair on carbon. Nitrogen only forms 3 bonds. Is that right? So how do you count? How do you count for nitrogen's bonds? There are 3 bonds, but then it should always have 1 lone pair on it. Does that make sense? Now these 3 bonds on nitrogen can be in 3 different directions, or it can be double bonded like that, or it can be triple bonded like that as it is in diatomic nitrogen. Yes or no? Does that make sense? It doesn't necessarily have to be in 4 different directions, but we need to have, for carbon 4 bonds, for nitrogen 3 bonds. Does that make sense? Oxygen will make only 2 bonds, which means how many lone pairs on oxygen? 2. It can be in 2 different directions, or it can be a double bond. Hydrogen will have only a bond pair, no lone pairs. Does that make sense? Okay? So let's do an example here. All right? So let's see, let's say I have the compound C2 hydrogen 6. The compound for which I have to draw the loose dot structure and predict the shape is C2 hydrogen 6. There isn't 1 carbon, there are 2 carbon atoms. All right? Let's count the valence electrons. So carbon will give 8 plus 6, which is 14. So I have to account for 14 valence electrons. All right? Whenever you have carbon will always go in the middle, and the other carbon will actually bond to this carbon. Now there are 6 hydrogens. How do you think you'll distribute the 6 hydrogens? 3 on each carbon. Does that make sense? 3 around each carbon. I need to have bonds between them. Is that right? Carbon, is it making 4 bonds? Is the other carbon also making 4 bonds? Let's count. 2, 4, 6, 8, 10, 12, 14. Have I counted for all my valence electrons? Now here is the important part that I introduced this molecule for. What is the shape of this molecule? When you talk about shapes, you talk about the shape around each central atom. Does that make sense? So Daniel, what is the shape around this carbon? How many bonds around it? Therefore the shape around C1 will be 4. The word is tetrahedral. C1. What about C2? Again, there are 4 bonds. So the bond around C1 and C2 will be tetrahedral. Are we good? Suppose I have an example, CH3OH. I have written it in a particular fashion, and I want you to pay attention to that when you do organic compounds. All right? So I have surrounded the first carbon with how many hydrogens? 3, and then there is oxygen. So probably the oxygen is bonding to the carbon. Does that make sense? There is an order to the madness. And then the hydrogen that is written after it is bonded to the oxygen. Alright? So carbon is 4, and counting you can add up. That's a 6. That's a 14. Alright? So when I write carbon, I will surround it with 3 hydrogens. Did I say that? CH3. Am I surrounding the carbon with the hydrogens? And then what is written after that? Oxygen. So I bond this to the oxygen. What is after oxygen? Hydrogen. What did the honk rule say? Carbon should have 4 bonds. Oxygen should have, if it has 2 bonds, what else should it have? 2 lone pairs. Let's count. 2, 4, 6, 8, 10, 12, 14. Have I drawn my Lewis-Dot structure? What is the shape of this molecule? Vishwa, what is the shape around C1?
That's gonna be a tetrahedral.
Tetrahedral. Oxygen is also in the middle. What do you think will be the shape on oxygen if it has 2 bond pairs and 2 lone pairs? It's going to be bent. Even though I have drawn it straight, the actual molecule will be bent there. This is methanol that moonshiners mix with ethanol and it causes blindness. Alright? Yes, Sam?
So in other words, if you were to answer this and say what the shape is, you put both.
Yes. For every atom in the middle, you'll have to say what the shape is. Yes. Doesn't matter. You can draw it straight as you draw Lewis-Dot structure. All I care about is you write the shape correctly. Because there are 2 lone pairs and there are 2 bond pairs. No question is ever stupid. Alright? So if I remove, there are 2 bond pairs. How many lone pairs? What does the lone pair do to the bond pairs? We only talk about the shape with respect to the bond pairs. It causes them to bend. Alright? So, we did a couple of carbon compounds. Let's now do ammonium. Alright? Ammonium is an ion. Alright? So my nitrogen has 5 valence electrons. Each hydrogen has 4. But there is a +1. If it's a positive ion or a cation, has it lost or has it gained? Lost. So what do you do with the count? You subtract 1. So how many valence electrons should you actually account for? 8. What will you put in the middle? Nitrogen. How many hydrogens are there? 4. Now remember, the honk rule is for carbon compounds. Only in carbon-containing compounds, nitrogen will have 3 bonds and a lone pair. This is not an organic compound. This is an inorganic compound. So what is the shape of this ion? It is Anna, come on in. Is there a pass? All right, thank you. Come on in. Thank you. Okay, so the shape will be what? 4 surrounding it, so it will be tetrahedral. And because this is an ion, there is one more aspect of it that you will have to follow. You'll have to put a square bracket around it and say it's a +1. Can my kids try phosphate and draw the Lewis-Dot structure of phosphate?
oxygen. Oh, wait, no, not 6, 7, 4, 32.
Okay? So phosphorus is 5. Each oxygen is 6, 4, 24. If it's a negative 3, what do you do? Plus 3. That makes it what? 32. What will go in the middle? So minus 8. How much am I to account for? 24. Alright? There are 4 oxygen atoms. Each needs how much more? 6 more. Yes or no? Can I just distribute 6 on each? And I'm done. Is that right? Why not? Which one has 7 electrons? No. Each bond pair is 2. Okay? So this one, I have to remember to put it in square brackets and put a negative 3 outside. Are we good? Alright. Besides these shapes, we have to know 2 more shapes. Okay? We have to know 2 more shapes. And I said only 4 elements follow the octet rule. Is that right? We are talking about non-metals, guys. Mostly non-metals form covalent bonds. Alright? Now, non-metal compounds come together and share their electrons. Is that right? Do not. So which are the elements that will break the 4 rule? So phosphorus, sulfur, selenium, tellurium, iodine. We're not talking about AT because it is so rare. Alright, it's radioactive. Can have more than 8. Can have more than 8. Why can't they have more than 8? If you look at group 2, there is only a 2s and a 2p orbital. If you count s plus p, 2 plus 6, no more than 8 for carbon, nitrogen, oxygen, and fluorine. But if you go from period 3 onwards, there is the S, the P, and the D. Even though the D is not filled in, kind of it's available as vacant orbitals in these elements. Therefore, they will all break, if necessary, the octet rule. Now, elements like boron, even though aluminum is a metal, sometimes it will form a covalent compound. We say there is a spectrum between ionic and covalent. Alright? It's strictly not metal and non-metal. Sometimes metal and non-metal can make a covalent compound too. Alright? Aluminum will fall in that category. Have 6 electrons around them. They don't go for the 8, they only have 6. Beryllium, even though it's a metal, because it's so high up in the periodic table, beryllium sometimes when it combines with elements like fluorine and chlorine, the bond will be covalent and not ionic. So beryllium will have how many around it if it bonds? Only 4. It breaks the rule. Alright? So here is an example of a compound, phosphorus pentachloride. Alright? If you count the number of valence electrons, phosphorus is 5, each chlorine is 7, 7 times 5 is 35, so my total number of electrons is 40. I have to account for 40 electrons. So when I draw the symmetrical arrangement, here is where I know to break the octet rule. There are 5 chlorines surrounding phosphorus. Is that right? It's okay for me to put all 5 chlorine surrounding phosphorus. Alright? And instead of making 4 bonds, make 5 bonds, which gives the central phosphorus 10 around it. It's breaking the octet. Alright? So if I get rid of my 10, I have to account for 30. There are 5, each needs 6. 6 5s are 30. And that is my Lewis dot structure. So the question is now, what's the shape of the molecule? Alright? So the shape is like this, and I'll show you what that is. Oh, I can't extend the page anymore. I've extended it so much. Okay. So let's say this is the shape of the molecule. The central phosphorus will have 3 in a plane. Imagine this to be a triangle that's on a flat plane. Are you with me? And then there is 1 chlorine at the top, 1 chlorine at the bottom. Alright? These 3 chlorine are on a flat triangle, 1 at the top, 1 at the bottom. Kind of there is a pyramid here. Does that make sense? There is a pyramid in the bottom and there is a pyramid at the top. So the shape is called trigonal bipyramidal. There are 2 pyramids. Let me show you what this looks like. Alright? And then you can see for yourself. So let's remove all this. Okay? So 1, 2, 3. Alright? Does it look flat like a triangle? Is it flat? Right? Is it flat like a triangle? Now I will introduce 1 more bond. It becomes tetrahedral, but then I introduce another bond. Let's rearrange this. Does this look like a triangle with the 1 on the top and 1 on the bottom? Do you see that structural arrangement? Or actually, I have this also that really helps with the understanding. I forget to pull that up. Okay, so here is my molecule. Yeah, I stole my daughter's. She had it when she was a little girl. Alright, so 3 as a flat triangle. You see that? And then 1 on top. Alright? And that makes a pyramid. Do you see that? Is that pyramidal in shape? And then 1 at the bottom. 1 at the bottom. Do you see that? That's also a base triangle, but then there is a pyramid at the bottom. Do you see that? Is everybody able to see the shape? So it's called, if you have 5 surrounding the central atom, what will be the shape of the molecule? Trigonal bipyramidal. Because it's at 5, the base is at 5. Right? Okay. I do have a number of hands up. Yes.
I have a question for that. Like the phosphorus, whatever those elements, what's the maximum phosphorus power? Did it bypass
You have to see what it is surrounded by. You'll have to draw.
what if it's like CL like 11?
You will be able to draw it and you'll be able to figure it out. I haven't seen shapes more than 12.
So if you have 12,
Then that saturation limit for compounds that we know around us. Yes, Melanie.
So you said boron and aluminum have 6
Yeah.
electrons. How?
That is when boron combines, say, if you form boron trihydride, to give an example. All right? So, if I form boron trihydride, boron is 3 plus 3, 6. boron and 3 hydrogens arranged around it. 1, 2, 3. You shouldn't be desperate and say, hey, do I need a double bond somewhere? There is no double bond formation possible. There are no more electrons. This arrangement is perfectly fine. It's a trigonal planar shape. Does that make sense? Yes, Anissa.
How it's part of the elements that can have more than 8.
Yeah?
So then how would it double bond it for the last one of these?
For the phosphate. For the phosphate one?
No,
This one? The phosphate ion?
No, the phosphate recording.
Where is that? Which question was that?
We just did that one.
Oh, okay. Good questions. All right. Why isn't it double bonded here? All right. There are some more rules. All right, that I will not follow in this class. All right. You have something called assigning the oxidation number and having the least oxidation number. I was told by Ms. Williams that even in AP chemistry they don't care about it anymore. I'm not going to teach that. If you Google these structures, probably you will see one of the lone pairs becoming a bond pair only because it gives it a lesser oxidation number. All right? But the shape will be the same. Doesn't matter what Lewis dot structure you draw. And it's the shape that impacts the molecule. Also, if you come to this one, all right, or actually the last example here, remember, elements are like human beings. They won't share until and unless they have to. All right? So it will not share, chlorine will not share its electrons. Or in other words, we haven't done electronegativity. The one that can keep the electrons more towards itself because of its nucleus capacity will keep it and will not give it away. That force has to be there to draw it out. Does that make sense? If I'm more powerful and I can keep the electrons with myself, you don't have the power, you don't get the electrons. Does that make sense? It depends on the nucleus's power with the two elements that are combining. Good questions. Nora kept having her hand up. Any questions? You understood what you had. Yes.
This is only with covalent compounds? It can't be with...
Covalent sharing of electrons takes place in covalent compounds. In ionic, you'll kind of do it, but then you show transfer of electrons. I'll show you 1 or 2 examples of ionic also. All right? So, yeah, you have to memorize shapes. Shapes and their names. Linear, bent, tetrahedral. All right? Trigonal planars. All these you will have to memorize. All right. So, let's go to the last example, SF6. Breaks the octet rule. SF6. Sulfur has 6. Fluorine has 7. 7 6 are? 7 times 6?
48.
48. Oh, that's it. You said about the 20.
You know, at this age, I've started making mistakes like this. At your age, what is the total? 48. What will go in the middle? Sulfur. So just surround it with fluorine. You accounted for 12. How many do you have to account for? 36. 6 6 are? 6 times 6 is 36. What is the shape of this molecule? All right? What will this molecule look like? So there is a square base. Are you with me? There is a square base. All right? And then, what do you see? So the square base has 4 bonds. Is that right? Everybody able to see that?
Extra 5.
And then there is one on the top and there is one on the bottom. Right? It's like, oh, there is a base squared, there is a pyramid on the top, there is a pyramid on the bottom. Does it make sense? Alright? So it's like, oh, there is a square base, one on top, one on the bottom. Each one is a fluorine. Alright? So this is, oh, there is a pyramid here, and there is a pyramid here. Alright? But the shape of this molecule is, it's called an octahedron. Why is it called an octahedron when there is surrounding 6?
8 sides.
8 faces. Like if you look at the faces, it has 8, and that's why it's called an octahedron. No. Octa means 8. You've already accounted for all 8 faces. 10 extend by again.
Okay.
Alright? The shape of this molecule is octahedron. Okay. So we do have a little bit of time. Alright? And what I would like my students to do is, you picked up this sheet of paper. Is that right? Now, I don't know, I have a lot of examples on the back. Yeah, it doesn't say state shapes, but what do I want you to do?
State shapes.
State the shapes. Alright? That's a lot. I'm not going to check homework. But let me tell you something. If you don't practice, you're going to fail next class's quiz. Okay? That's a guarantee. If you don't practice, you won't be able to do those dot structures. Can I have students start this on a notebook paper right now in class?